Thanks, Misha. And thanks to the organizers. It's a pleasure to be here. Very nice conference indeed. And so the talk is based on joint work with Pavlo Pylyavskyy, and it's very much ongoing. So many things we still don't understand very well. And it will be sort of continuation of Sergey's talk to some extent. In particular, Rick asked so Sergey was talking about some incidences and bipartite graphs, and Rick asked what this has to do with the dimer model. So I'll try to answer that to some extent. And we'll see in what Sergey described, in some cases there are some remnants of the dimer model there already, but in general we'll need to upgrade his model a little bit. So, and actually this was motivated, and yeah, so in what Sergey was describing were some incidence theorems, and these theorems were sort of static theorems. You have a configuration of points and lines. There is no dynamics there. So what I'll discuss is could be thought of as dynamical versions of this. So imagine you have some configuration of points and lines, some incidence. And this incidence, it will have a property that it will be able to reproduce itself. So we'll do something to that configuration. We'll get a new configuration, which is combinatorially the same. So, okay, so this, and I'm not going to do slides. I'll just show you a little mathematical presentation, and then I'll do a board talk. So this is a theorem that sort of motivated this work. And this is actually something we almost saw in Sergey's talk. So he had this twin stars of David example, which demonstrates his theorem. This is just going to be a 5-pointed version of that. So recall what it looks like. So in his case, he had a hexagon. I'll take a pentagon, but really it doesn't matter. I'll say later why I want a pentagon. So, and what we're going to do is we're going to draw the diagonals of this pentagon, and we're going to take them as sides of a new pentagon. So now we have two pentagons, one large one and one small one. And we consider the following configuration. So we have now another pentagon, the big red one, and it has a property that its vertices lie on the sides of the blue one. And then when we construct the small red pentagon in exactly the same way as we did for the blue one, then imagine it so happens that its vertices again lie on the sides of the small blue pentagon, which is a non-trivial condition. In general, there's no way that's going to happen. And this is actually a particular case of what Sergey was describing. So we do see an incidence here. Some lines, triples of lines meet at certain points. And this corresponds to a tiling of a torus with 10 quadrilateral tiles. And what Sergey's theorem is saying here is that, well, we do have 10 incidences here. So these incidences, they happen at vertices of two red pentagons. And if 9 of them are satisfied, then the 10th is satisfied as well. I actually want to take a slightly different perspective on Sergey's theorem here. Oh, Sergey, sorry, I didn't mean Sergey's theorem. I meant theorem from Sergey's talk. Yes, it is of course joint. And everything I'm going to say is joined with Pasha as well. So Pasha is here during. So, okay. So what Sergey and Pasha's theorem is telling us in this case, so imagine we have the blue pentagon already. So we have this big one, then we can construct the small one, and then we want to reconstruct the configuration. So we want to find the red pentagon so that this incidence holds. And for that, we need to choose 5 points. These are the 5 vertices of the big red pentagon. Because there are 5 points in the plane, we have 10 parameters to play with. And then we also have 10 incidences that need to be satisfied. So it's these points lie on the sides of this. Same here. So we have 10 equations on 10 parameters. But actually, Sergey explained, one of the 10 equations follows from the other 9 equations. So there is a one, the way you can interpret the theorem in this case is that there is a one parametric family of solutions, which you can actually see. So the red thing can slide along the blue one because there is a one parametric family of such. And so this is still not the theorem that I wanted to tell you about. But one thing to mention here is, so why I'm doing this mathematical presentation is because I cannot draw this. I cannot draw this because you see above there's some elliptic curve there. So this code here is based on elliptic functions. There's no way you can draw by hand something that comes from elliptic functions. So actually, well, we see that there is a one parametric family of these red pentagons here. This family is parameterized by an elliptic curve. This curve has something to do with the spectral curve of the dimer model on that graph with 10 tiles on a torus. But I'll get to that later. But the theorem here is the following. So we have, so suppose we have this incidence that the vertices of the big red pentagon lie on the sides of the big blue one. Same for small pentagons. And then we can iterate this. So for the small blue and small red, we can again take the diagonals, produce even smaller pentagons. And the claim is that the incidence is actually going to reproduce. So if we repeat, then for the smallest red pentagon, its vertices again lie on the sides of the small blue pentagon. And therefore, it of course continues forever, because then you can apply that statement to these two pentagons. And then if you stare at this for long enough, you'll be able to see that this is actually 5 applications of Desargues theorem. I don't know if you can see it right away. I can't. Or you can use that software that Sergey advertised that can prove theorems automatically. I'm sure you will see that. So the theorem is not hard. And actually, these polygons here, they don't have to be pentagons. Any number of vertices is fine. I took pentagons because I wanted elliptic functions. I don't want higher genus theta functions or anything like that. So the theorem is pretty simple, but again, as in the previous talk, our goal here is to understand the general combinatorial framework that underlies this. And as I was saying, so here, this is an instance of sort of a dynamical incidence theorem. We have an incidence, and then we do something to that incidence, and it reproduces. Like the way this two smaller pentagons look like combinatorially, it's the same thing as we have for the two bigger ones. And so I will describe a combinatorial framework that underlies this type of phenomena. And also at the end, I'll talk a little bit about this parameterization question that I mentioned. You fix the blue pentagon, and you want to know how can you choose the red one, what's it parameterized by, and this, as I said, has something to do with the spectral curve of the dimer model. So now I have to get rid of the screen, and I think there I press chalkboard. Chalk talk. Oh, yes?
When you were moving your blue pointer around, it seemed like you were all around the big pentagon.
So yes, the blue pentagon was fixed, and then the red has sort of an ability to flow around. Yes, so I can, there is a one parametric family of this red one, so the vertices of the red one, they slide along the sides of the blue.
I see, but there's for each point on the red pentagon, there's a unique blue pentagon.
So if it was unique, then this would be a rational curve parameterized by a side, but no, it's an elliptic curve. But if everything is convex and we want real solutions, then, well, from this program, I see it's unique. And it's probably not very hard to prove some small argument with elliptic curves. But in general, if it's in the CP2, then no, it's not unique. One can calculate the degree of that map, but it's not unique. Yes?
Have you had to compare that to like a paper that I have with Sanjay and Terence, this R matrix stuff for DCT map and so on? So I have a paper with Anton, with Sanjay and Terence. And this example you just showed is essentially...
Which paper?
I forgot the name, because we changed the name a few times.
Okay, yeah, no, okay, yeah, I think I know what paper you are talking about. No, I don't know how this is related to the stuff from your paper, but we can discuss later. Okay, so, but I want to explain what this has to do with the dimer model. So basically, oh, sorry. So let me start with reminding you some stuff about the dimer model, and I'm gonna take a dynamical perspective on the dimer model. So this comes from the Goncharov-Kenyon paper, where they describe dynamical systems, actually integrable systems that are based on the dimer model. So the construction is as follows. So you consider a bipartite graph. And it's going to be a bipartite graph with weighted edges. For the moment, you can think of a planar graph. Later, it will be graph on a surface. Really doesn't matter. So on this kind of bipartite graphs, so if we have weights on edges, then we can look at the partition function for the dimer model, which is the sum of weights of all dimer covers. And there are these standard moves that you can do to the graphs which do not change the partition function. The most fundamental move is the square move or the spider move or the urban renewal, I guess, is the version that is the most general. So you have a quadrilateral face of your graph. You have some weights written here, and then you update the graph in the following way. So what you do is you remove the four edges of this quadrilateral, you keep other edges intact, and then here you create a new quadrilateral like that, and you join the vertices in the following manner. So this is an update of the graph, and here the weights are going to be 1, 1, 1, and 1, but it doesn't matter because there's this gauge invariance in the dimer model. And then if you want the partition function to be preserved, you can calculate what weights you need to put here. These are some simple rational expressions of x, y, z, and w. The form is unique and just follows from the fact that you want the sum of weights of dimer covers to be preserved. And then the way and there are some other simpler moves, like you can contract two valent vertices, things like that. And then the way this Goncharov-Kenyon systems work is that you start with a graph, and that graph is supposed to be on a torus, and you're doing moves. And when you're doing moves, the graph changes and the weights change. And then at some point, it might happen that you get the initial graph. Combinatorially, you get a graph that's the same as the initial one, but the weights are going to update. So you can view this as a dynamical system. It's a certain mapping of weights. And so the nice feature of this, clearly this preserves the partition function, but also because the moves are local, and if your graph is on a torus, it preserves more than just the partition function. Specifically, you can count you can add up the weights of dimer covers that belong to the same homology class. That's going to be preserved by locality, which is the same. So Thomas yesterday introduced the spectral curve of the dimer model. I'm going to get to that later. But equivalently, it can be said if this is happening on the torus, then the spectral curve is preserved. So it's an example of a dynamical system which is isospectral, and then it has some very nice properties. So one can prove, and Rick and Goncharov, they prove in their paper that, so you have this curve that's preserved, and then the dynamics that's happening can be viewed as a linear dynamics in the space of line bundles over the curve. It's an example of an integrable dynamical system that's based on this dimer model. And also you can interpret this dynamics, and which is based on the moves or just the moves themselves in a geometric way. So this is something which is described in the paper of Pasha, Sanjay, Niklas, and Max Glick, which is called vector relation configurations. So they talk about assigning vectors to vertices of the graph in that paper. I actually want to assign points in the projective space, but it doesn't matter because like if you have points in the projective space, you can lift them to an affine space, they become vectors. So they also have, they have two perspectives in the paper. I'm going to describe the projective one. So what do you do if you have this bipartite graph? So to every black vertex of the graph, you're going to assign a point in a projective space of certain dimension. The dimension is the same for all vertices, and the condition that this is supposed to satisfy is the condition that if you look at all neighbors of a given white vertex, then these neighbors are linearly dependent. So for instance, for three valent vertices, what it means is that these three black points lie on the same line. If you had 4 points, so they're supposed to form like a circuit, a minimal linear dependent set. So you can consider some configurations, and then one can observe that this model is consistent with these moves in the sense that if here you associate points to black vertices in such a way that this condition is satisfied, then there is a unique way to perform the move so that the condition is still satisfied. It's easy to, the thing you put at this black vertex is going to be an intersection of something and something else. You can just see what that should be from the condition. And actually, it's not just a coincidence, but it's actually the same dynamics. The way you can identify them is you lift these points to vectors, and then the condition will be that these vectors satisfy a linear relation. You take the coefficients of that. This gives you weights on edges. These are not quite the same as these weights. These are what's called Castellane weights. You need to multiply them by Castellane signs, twist them a little bit, and then the two dynamics, they agree with each other. The way, so when you do this intersection operation, in terms of points, if you look at what happens to coefficients of linear dependence, well, there's some rational transformation coming from solving some linear system. It's just exactly the same transformation. So this is basically, and it's not exactly a one-to-one correspondence, but this is sort of a geometric version of this Goncharov-Kenyon dynamics. And what I will describe is basically a model that unifies this idea and what Sergey was describing. And the reason one would, it is, if you actually want to incorporate the things from the dimer model into Sergey and Pasha's work, you may want to do this square moves or urban renewals, and then you'll see that, well, in general, this doesn't work. So if you have sort of a tiling on a torus, you try to do these moves, then the conditions that they just break down. So we'll enrich the model. We'll take some features from here and some features from Sergey and Pasha's model, and then we'll see that this will behave nicely under moves, and this will give us this dynamical incidence theorems like the one I showed you in the beginning. So let me describe and again, the main theorem is gonna be, again, the same kind of theorem as in the previous talk, which is definitely not the hardest part. If there is a hard part here, then that's definitely not the main theorem. It's, again, pretty straightforward to verify. Don't even know if you can call that a theorem. So the model is as follows. So suppose you have a bipartite graph, and it's gonna be on the torus, but in principle it doesn't have to be, it can be on any surface. And now, just as Sergey did, so what we're gonna do, we're gonna to black vertices, we're gonna assign points, to white vertices, we're gonna assign hyperplanes, just as in the previous talk. So points here and hyperplanes to white vertices. And they are all in the same projective space. We're gonna impose some conditions on this. So the conditions at the white vertices are the same as the one I mentioned before. So the neighbors are supposed to form a circuit. So it's a minimal linear dependent set. So for instance, if we have 3 valent white vertex, then these 3 black points are supposed to be on the same line. And if we look at black vertices, yes? No. Well, so far it has nothing to do with the hyperplane in the center. There will be some compatibility condition, yes, but that will come later. So there will be conditions at vertices and conditions at faces. Conditions at vertices are just that, well, the neighbors of a white vertex, they are supposed to form a circuit. So in this case, if you associate 3 points to these things, they lie on a line. So for black, it's the same condition, or the dual of this condition. So these 3 hyperplanes, they're also supposed to form a circuit. So what that means, so if the dimension is 2, it's just 3 lines meet at a point. Well, basically, the way you can think of hyperplanes is that they're points in the dual projective space. You impose exactly the same condition on those points. So we could actually phrase it as one single condition. So the condition is that neighbors of any vertex form a circuit. It kind of look differently depending on whether the vertex is white or black, but it's the same condition. So it's so a circuit means that they're linearly dependent, but in sort of a minimal way. So if it's 3 points, they are on a line, but they do not coincide with each other. But this is just a general position assumption, doesn't matter that much. We could just say that they're linearly dependent, and then think of everything in some kind of a birational way. So, yes?
So if your projective space is of degree like 3, if dimension 3, and you have a vertex with 5 neighbors.
That's bad. Because then there are no circuits of that size. Yes. So this will, so this means that, not all the dimensions are possible. We'll talk about this later on. So in contrast to in the previous talk, the dimension could be arbitrary. So here, in some dimensions, this configuration is just not going to exist. So that's condition 1. So the second condition, well, that's the condition from the previous talk. In the previous talk, Sergey talked about quadrilateral tiles, but it actually doesn't matter because, as was mentioned, this coherence condition on the tiles, well, you can state it geometrically. So if you have this quadrilateral tile, the condition was that two lines associated to this and the line through these 2 points, they meet at a single point. But that's the same as to say that if you take the multi-ratio around a face, the multi-ratio is equal to 1. Therefore, this condition, it can actually be imposed on any face. It doesn't have to be quadrilateral. It's still a geometric condition. So if you have a hexagonal face, the condition is that you can actually subdivide that into quadrilaterals so that in each quadrilateral, the coherence will hold. So the condition is that all faces are coherent. And, well, what that means is that the multi-ratio around every face is equal to 1. So let's consider configurations with that property and then a simple theorem or a proposition is that these conditions, they actually survive the Daimer model moves. So if you just assume that the faces are coherent, the Daimer model moves are not going to work, so the coherence is not going to be preserved. But if you impose both kinds of conditions, yeah, what does it mean survive the Daimer model moves? First of all, of course, one needs to explain how to do these moves. But this we actually already know because, well, before I explained that if you assign points to black vertices, nothing to white vertices, then, yeah, there is a way to propagate this through moves. And here, well, we have a law of propagation for black vertices, so we're going to apply that. Same rule for white vertices, just because there's no difference between black and white. Right? You can recover, go from the space to the dual space, and so on. But the point is that this condition is going to be preserved. So if all faces were coherent, then they're actually going to stay. So that's the statement. The statement is very simple. It's, I don't know, like maybe I couldn't phrase the proof in one line as was for Desargues and Pappus theorem, but 2 lines would probably be sufficient. You can verify this yourself. I think I'll skip the proof. And then that theorem that I showed in the beginning, that's actually a particular case of that. So you can, if you take a torus, so the tiling is just 10, take 10 squares in a row like this. You glue the opposite sides, then you glue this and that, but with a twist. So because you cannot just glue them, it's in black and white, you cannot glue them together. So you twist it appropriately, you glue, you get a tiling on a torus. So you impose these conditions, and actually in this case, so if the dimension is 2, and all vertices are 4 valent, and more generally, if we have a square grid, and the dimension is 2, then the circuit condition becomes trivial, because then it just says that 4 points form a circuit, a minimally linearly dependent set, but for 4 points in the plane, that doesn't mean anything. And as Pasha was suggesting, for 5 points in the plane, that would be impossible. 4 points is the maximum you can have, but then it doesn't mean anything. So, which means that on this graph, the only condition that we have is that all faces are coherent. And this gives us a configuration with 4 pentagons that I showed you in the beginning. And then the reason it propagates is because, well, the conditions are going to be preserved when we do the moves. And the way you do the moves here is something like you do the urban renewal at every second phase, then you contract 2 valent vertices. Yes?
Can you explain how you glue these things together to make a torus again?
Sure. So we have 10 squares, and it's bipartite. So you would, I believe, you would identify this vertex with this one. So in the vertical, you just glue them in a straightforward way, which works, right? Because you have an even number. And then this you would glue with a shift of 3.
And the claim is that this is a genus 1 surface?
You mean the surface? The surface is a torus.
No, but I mean the spectral curve is genus 1?
The spectral curve.
Something elliptic in the...
Yes, but yeah, I'll get to that. But it is. If you look at the Newton polygon, you would think it's genus 3 or something. But there is. So we have a closed pentagon. It brings the genus down to 1. I think Mariana had a question. So.
What is in this story, where are the edge weights change involved?
So the edge weights again. So with the edge weights, it's a little tricky. Because this, if we just look at the black vertices, then the neighbors of every white vertex, they're linearly dependent. We can find the coefficients of linear dependence. This will give us one collection of edge weights. They propagate the way they should be. So the dynamics on them is the usual dynamics under urban renewals. But there is another set of weights which is a priori completely unrelated to that. That comes from the white vertices. That will also propagate in a nice way. But you sort of have two different, two different dimer models sitting on that graph. But there is a compatibility condition on them. And that condition actually survives under that dynamics.
Is there some kind of duality between these two?
I don't hear you.
Is there some kind of duality between these two collections of weights? If you have one, can you derive the other in a more or less unique way?
So let me get to that. Well, first of all, it cannot be unique because as we saw in the Mathematica thing I was showing, if you have the blue pentagon, it gives you a one-parametric family of red ones. So the blue pentagon are things that are sitting at black vertices here. The red one, if you look at the sides of the red one there, are things that are sitting at white vertices here. So, yes.
In the case where you have valence 4, so that the first condition disappears.
It disappears, but it kind of reappears after you do the moves, right? Because you have 4 valent vertices, then you do an urban renewal, you start getting 3 valent vertices. So it reappears again.
Okay, so my question was that maybe...
But initially it's trivial.
Right. So my question was, but I'm not sure I want to ask it. I'll try still. Is this going to be an instance of some kind of sequence of cluster transformations for y, like for for the Poisson cluster? Right.
Well, it definitely is because again, if you look at edge weights, that's just the usual Goncharov-Kenyon dynamics. Right. But we kind of have 2 different collections of edge weights. On each of them, yeah, if you think of phase weights, we have cluster transformations going on. So we have 2 collections of cluster variables. They are compatible in a certain way through this coherence condition, which I guess is hard to phrase in those terms. I don't know what it looks like algebraically. And the claim is that when you mutate, the compatibility condition remains. Does that make sense?
So it's like 2 clusters that are coupled in some way to each other.
Yes.
And they move sort of, the marriage survives
That's right.
the urban renewal.
That is correct. Okay, so that was sort of that trivial main statement that I promised. So now, if there are no other questions, I'm gonna go back to that problem we discussed in the beginning, or not the problem, but this fact that we have this one parametric family of red pentagons inscribed in a blue one. So in this language, this corresponds to the following problem. So here we have this configuration with things assigned to black vertices and white vertices. So suppose that we know things assigned to black vertices. We have a collection of points assigned to black vertices. Can we recover things that are assigned to white vertices? Can we recover what's coupled with that? And in terms of that Mathematica program, the question is, to what extent can we recover the red pentagon from the blue one? And we saw already that, well, it's not unique. We have a one-parametric family. So you can treat this question very naively. You can count the number of unknowns and the number of equations. So the unknowns are the hyperplanes sitting at white vertices. And the equations are, there are two kinds of equations. There are equations at black vertices. These are the circuit equations. And there are equations at faces, which are coherence equations. And this gives you some nonlinear system on the coordinates of hyperplanes. And well, if you count super naively, well, the first thing you'll see is, well, when you do this count, there is the Euler characteristic of the surface that's showing up clearly because we have equations at vertices and faces. And the number of degrees of freedom that you have, the dimension of the space of solutions increases as the genus of the surface increases. And a naive count shows that for the torus, there is the same number of equations as unknowns. But actually, one of the equations is redundant. This is exactly the theorem from the previous talk. The theorem says that if the coherence conditions are satisfied at all but one phase, then it's also satisfied at the remaining phase. So one of the equations you remove, which leaves us with n-1 equations on n unknowns, which sort of suggests that this should be an algebraic curve. Of course, in general, we cannot make such claims, and this is very hard to verify. But at least in some cases, or maybe in the general cases. So ideally, what I would want to be able to say is that, well, that curve is exactly the spectral curve of the underlying diamond model. In general, that's not even true. Conjecturally, this is true for a large class of graphs. But what is always true is that there is always a map between the two curves. What we don't know is whether that map is birational in all reasonable cases or is something else. So let me explain where the spectral curve comes from. And so I still have something like 10 minutes. OK. So first of all, just to remind you what a spectral curve is. So if you have a bipartite graph, so the spectral curve, you can define it in many different ways. We saw one definition in Thomas's talk yesterday where he considered this magnetically altered Castellane matrix, which is a Castellane matrix with two parameters in it. You take the determinant, that's the spectral curve. Another way to think about the spectral curve, so you have a bipartite graph that lives on a torus. So then you can, for each homology class on the torus, you can add up the weights of all perfect matchings in that class. That gives you a collection of partition functions. So your partition functions are going to be indexed by two indices, I and j. I is sort of the number of times you go around the torus in one direction, j is the other direction. So you form a generating function out of those. For some topological reasons, you need a sign here, which is something like this. And you sum over all ij. This is actually a finite sum because you have a finite number of diamond covers. So, and you set this to 0. This is an algebraic curve that's called the spectral curve of the dimer model. That is the same curve that was in Thomas's talk yesterday, because Castelline's theorem applied to the torus exactly says that this is the determinant of the Castelline matrix. So, so this is the spectral curve. So now what does the spectral curve have to do with our problem? So we have this graph that sits on the torus, and we have hyperplanes sitting at white vertices. We have points sitting at black vertices. And on all faces, we have coherence conditions. So as Sergey explained, the coherence condition is some kind of a co-cycle condition. So the product, the alternating product of some numbers around the face, this product is equal to 1 for all faces. So what this means is that, well, now you can start taking the same products, but over arbitrary cycles on the torus. They don't have to bound faces. And then the product will, because around every face it's 1, the product will actually only depend on the homology class. So what you can do now, you take a torus, you take a basis of cycles. So for any configuration like this with coherent faces, you can compute two numbers, lambda and mu. These are these multi-ratios that are taken along global cycles. And this do not depend on what cycles you take, only depends on the homology. And then, well, what we can do to black points, because we know that the black vertices that correspond points, recall that we can take coefficients of linear equations that they satisfy. This give us, well, twist them by Castelline signs. This gives us edge weights. So we can construct the spectral curve. So a simple exercise is that, well, these two multi-ratios along global cycles, they actually are not arbitrary. They satisfy a polynomial relation. The relation is exactly this. So if you compute, if you have this configuration with coherent faces, you compute multi-ratios along global cycles, then the claim is that the pair of numbers that you get, it lies on the spectral curve. So therefore, and the way we can think about this is as follows. So we fix the points. So to black vertices we associate points. We fix this. So after we fix this, we can construct, we have the spectral curve, because this gives us edge weights. So from this, we can construct the spectral curve. And now we want to find the hyperplanes that can be associated to white vertices so that all our conditions are satisfied. We can look at the set of all possible choices of things that we associate to white vertices. And for every choice, we get a point on the spectral curve. The way it works is that, well, if we have such a choice, so now we have points associated to black vertices, we have hyperplanes associated to white vertices, we can compute these multi-ratios along global cycles. That's a point on the spectral curve. Therefore, we have a map which goes from the set of possible choices of things sitting at white vertices to the spectral curve. And so we started with the dimension count. It seems like this should be one-dimensional from counting equations. This is also one-dimensional. So ideally, one would want to show that, well, that's a birational map between these two curves. There is no way this can be true in full generality. You can construct examples of some stupid degenerate graphs when this is an empty set, for instance. But the conjecture is that, and also this depends on the dimension. So as Pasha mentioned, the dimension cannot be too high if you go to, actually too low, because if you have vertices which have very high valence, then the dimension cannot be too low. So too low dimensions are bad. And then if you go to dimensions that are too high, then apparently this map, it's a covering of some high degree. But conjecturally, there is always some critical dimension when this is a nice birational map. This is, for instance, what happens for a square lattice. If you have a square lattice graph, the dimension is equal to 2, then it's very easy to verify that this is a birational map. It's actually just the proof is that, well, all your vertices are 4-valent. You fix a point on the spectral curve, then because of the 4-valency condition, you just get linear equations at each black vertex. The number is the same as the number of unknowns. You're done. And the problem with general graphs is that different vertices have different valences. So vertices that have high valences, at this vertex, yes?
Sorry, when you say square lattice, you mean modular some?
Square lattice yeah, you take square lattice in the plane, you take some parallelogram with integer vertices. This gives you a graph on a torus. So for such a graph, if you take the dimension to be 2, then this is a birational map. The proof is simple because it's very regular. So in general, we do get a nonlinear system. In this case, it becomes a linear system. So for more general graphs, it doesn't work that easy because you might have vertices of different valence. But what you can do sometimes, in many cases, if you have a vertex whose valence is small, you can do moves and increase the valence. And if you are able to actually increase it by a sufficient amount, then you can use this to prove that the map is birational. And the question is sort of reduces to the question for which bipartite graphs on a torus you can always do moves so that for any a priori fixed vertex you can increase the valence to some specific number. And it seems like maybe for all minimal graphs this is possible, but we are not quite sure. It might be a more restrictive class of graphs. But for all reasonable examples, this works. So in some dimension, it's a birational map. And there are, reasonable examples are examples that correspond to some interesting dynamical systems. And so I mentioned this example with pentagons. That's not at all the only example. There are many other sort of dynamical incidence theorems that you can deduce from this. So for instance, since this was something mentioned in the previous talk, so some theorems from Bobenko-Suri's book are also particular cases of this construction. And yeah, I think I'll stop here.